Okay, so let's leave this here for a moment and let's see what happens with this probability distribution and what can we say about it. We can actually say a great deal about it just thinking about the idea that the system is in thermal equilibrium, therefore it's homogeneous and it's also isotropic, so it looks the same in any direction. So, okay, this probability distribution, as I said before, depends on the components of the velocity, vx, vy, vz, and what seems reasonable, and here I'm following the original reasoning of James Clerk Maxwell in 1860, or rather the retelling of this that Sommerfeld has in the book, so this is in the thermodynamics book by Sommerfeld if you want to look at it. This probability distribution has to factorize. Okay, and the logic of this is that, well, it doesn't really make sense to think that the probability of finding a particle with a velocity component x between vx and vx plus dvx has anything to do with the probability that the velocity in the y component has a velocity between vy and vy plus dvy, or vz and vz plus dvz. So this the probability that the velocity in any given component has any value should be independent of the value of the other components of the velocity. Okay, and that sounds like a reasonable criterion, and this has a consequence, which is that the probability distribution has to factorize. Okay, so it's going to be written as a product of, well, in the lecture notes I can actually make some sort of nicer letters that I can do by hand. So this is some sort of calligraphic p, and this is some sort of calligraphic lowercase p, if you like, px of bx, and the same thing py vy, and the same thing pz, calligraphic p, lowercase pz, vz. Okay, so actually, because we know that the system is in equilibrium, it's not only homogeneous but also isotropic. So like I said just now, it should look the same in any direction. So this means that the probability of having any specific value of the x component of the velocity should be the same in the x direction than in the y direction than in the z direction. So these probabilities, x, y, and z, should actually be the same thing, so the same function, right? That's another reasonable thing to require. And another thing that this is really clearly necessary is that if I choose to work with this specific reference system, x, y, and z, okay, so that the velocity v rides with these specific components, x, y, and z, vz, then if I decide to choose a different rotated system like this one, okay, where I call this, I don't know, like this phi and eta and zeta, something like this, then, you know, the same velocity vector would have different components, of course. Let's just write it like this, that, and eta, and zeta. It is the same velocity. I just changed the way in which I write the velocity because I just arbitrarily chose any other different reference system. But as I said before, you know, there's no privileged directions and everything is isotropic. So this probability should be independent on any specific system of axes that I choose to write my velocity vectors. Okay, so what I'm saying is that the probability of finding a particle with velocity components x, y, and z in the xyz reference frame should be the same, and the probability of finding a particle with components chi and eta and zeta in the chi, zeta, eta reference frame. These two things should be the same. Of course, they are the same, right? So if these have to be the same for any choice of axis, it is clear that this probability cannot depend on the different components alone, but it actually has to depend on the modulus of the vector. Because one thing, even if these components, of course, change as you change the reference system, the size of the vector, which is sitting here, remains the same. What it means is that vx squared plus vy squared plus vz squared is going to be equal to v psi squared plus v eta squared plus v zeta squared, or any other, the composition of the vector in any of the different reference system you like. So what this means is that the probability depends on the modulus of the velocity. It must depend only on the modulus. It cannot depend on individual components. And it has to factorize. And the different factors have to be identical. Okay? So with these stringent constraints in the probability distribution, there's only one possible function that can do that. And we are going to do that later, but that's of course exponential. But we are going to do this in the very end of this lecture. So just write out the explicit formula for this probability distribution. One important consequence of this fact that the probability distribution depends only on the modulus, or if you like, I can just write it out explicitly like this. So like this. Copy, paste. There you go. So one, if you want, I can put the square root here. Right? It really doesn't matter, but the point is that if I ask myself of the probability of this, y and z, and the probability of reversing the velocity in the z component, that is, what is the probability of finding particles that come into the wall compared to the probability of finding particles that go away from the wall with the same modulus in the velocity, it has to be the same, okay, because these two vectors have the same modulus. I don't care if this sign is negative because it's going to appear square in the argument of the function. Okay, so it's equally likely to find a particle with velocity v that is coming into the wall than it is to find a particle with the same velocity going away from the wall. Okay, so with all this that we have learned about the probability distribution p, we can come back to where we were before. I'm just going to copy this and bring it to where I have space to write. So just bear with me a second, make a new page. There we go. Okay, so remember what we had here. Okay, so our problem was we have the walls of the container and we want to know what is the total momentum that is being transferred per unit time by all the particles that are colliding with the wall in an infinitesimal time interval dt. Okay, and we are looking specifically at a differential surface element of this wall of area d sigma. So one thing that I actually didn't write is that in this formula here, I'm counting all the particles in the cylinder, in this slanted cylinder, that have velocity between v and v plus dv, but these particles have velocities that are both incoming and outgoing. Okay, I haven't specified here that I'm only interested in particles that are coming into the wall. Okay, so let's just do that and choose a sign for vz. Okay, I'm going to require that vz is positive. Okay, so that's just one direction. And the particles with the vz negative are just, in this criterion going away from the wall. This actually does not coincide with the choice of axis that I did before, but it really doesn't matter. I can put here my smaller than if you like. It really doesn't make a difference because everything is symmetric. But anyway, just to be consistent with what I wrote in the lecture notes, we have vz positive. So fine, let's just calculate then the pressure. What the pressure is going to be, or the infinitesimal contribution of these particles with that specific velocity to the total pressure, is the force divided by this sigma. Okay, and this is, if I just get rid of the things that cancel out and so on, and p, the probability distribution of px, vy, and vz. And then there is this vz and this vz, so I have the vz squared here and the volume element in the velocity space. Okay, so now if I want the actual pressure, I have to integrate this expression for all velocities and not just for that specific velocity. So what do I do then? 2m and p, and here is the integral, and here I have to break down the integral. Okay, so I am integrating in vx, vy, and vz. So this is in vx, I integrate from minus infinity to plus infinity. In vy, I integrate from minus infinity to plus infinity. And in vz, like I said before, I integrate either in the positives or the negative side, let's say the positive side, from 0 to infinity, dv set. Okay, because I want the particles that are incoming, and I don't care about the ones that are going away, because these are not going to collide with my wall and are not going to transfer any momentum. So this is again probability distribution bx, by, v set, and v set squared. Okay, so here we can do a little trick using this symmetry property that we learned. Where are we? Oh, okay. So here we learned the symmetry property that if I reverse the sign of the velocity in one specific component, the probability distribution is identical. It doesn't change because it really depends on the modulus. So I can use this here to simplify this expression a little bit. So bear with me a second. I can write this as the integral from minus infinity to plus infinity dvx, integral from minus infinity to plus infinity dvy. And here let's just make a big bracket, and I have the integral from 0 to infinity dv set. Let's just write 1/2, well, I will write it down here, 1/2 of the integral from 0 to infinity dv set be vx, vy, and v set squared, plus the same thing. Okay, that's why I put the 1/2. I'm just repeating this twice. Okay, making it smaller so that it fits. Sorry for that. Well, I don't know what to do now. Yep. Let's just make it smaller so that it just fits like this. Okay, so I copy. Just wanted to save time in the end and spending more time in writing it down. Okay, there you go. So you have it twice, but you have the 1/2, so it should be the same thing. Now in this first one, let's change the variable v set to minus v set. Okay, if you do that, well, what happens to the limits of integration? They remain the same, but this is minus. The v set gets a minus sign, and here the probability distribution gets a minus sign in the z direction. V set is squared, so it doesn't change. But remember, this probability distribution is the same as the probability distribution with the positive sign, because we said before. And this minus sign here, I can be used to swap the order of the integral of the limits of integration, like this. Okay, so what we have in the bracket actually is the integral from minus infinity to plus infinity of the probability distribution v set squared. Okay, so overall, what we have is m and p, and here is the full integral from plus infinity to minus infinity of d cube v, so all the components x, y, and z as well, of the probability distribution once again, y and z, and then v set squared. Okay, so here just remembering about probability distributions from mathematics with physical applications or whatever, you see there is a probability distribution here, is integrated over all the space of this random variable, and here is v set. Well, this is the thing that I'm averaging, and this integral is an average of that thing. So I can just write that or define that to be m times np times the average of v squared, written like that, average with the over bar. Okay, so this is, this is the result. Remember, the initial thing was the pressure. So what I'm writing here is that the pressure in my system is simply proportional to the average velocity in the component which is perpendicular to the wall that I'm looking at, to any wall. And remember that my system is isotropic, so actually v set squared average should be equal to vx squared average and by squared average, and actually any other direction. And this is also 1/3 of the average of the modulus of the velocity. Okay, because the modulus is bx squared plus by squared plus bz squared. So what you have here is 1/3 of m np, and here you have the average of the squared of the modulus of the velocity. Okay, so that's the pressure in a system made of point-like particles, like we were discussing. So in a kinetic model for an ideal gas, this is what the pressure is. So here you have kinematic thing, average velocity, and here you have a thermodynamic thing, pressure. Okay, that's the beauty of it. Then you can just also remember that the kinetic energy, right, of a particle is going to be equal to 1/2 of the mass and the modulus of the velocity. And if you take average, that's what you get. Okay, so here you get this one, but in this case is 1/3 of the average of the velocity. But you can somehow sneak in here in this expression for the pressure the average kinetic energy per molecule. Okay, so then we can do that and say this is 1/3 of m and p, and then this v squared is 2 the average kinetic energy of the system divided by the mass of the particle. So the mass goes with the mass, and what you get is 2/3 of the homogeneous density of molecules in your system times the average kinetic energy per molecule. Okay, so that's the final expression. It's a direct link between the pressure, like a variable of state in thermodynamics, and the average kinetic energy per molecule of the molecules that make up the gas of your system. Okay, so that's the first result. That would be pressure. Okay, so now we know what, according to kinetic theory, pressure is. Now, what can we say about temperature? And here we have to lean on thermodynamics. So it's actually not a self-contained thing. We have to know what the equation of state of an ideal gas is, and we have to know what temperature is from thermodynamics. We just want to connect somehow temperature with the average kinetic energy in our system. And the way to do that is to, well, first, let's assume that you have 1 mole of substance, okay, in your system. So let's just take the product of pressure and the volume occupied by your gas, which is 1 mole of gas. So what you have there is 2/3 of the volume, which I don't know what it is, times Np E kinetic. Okay, that's just copying from the expression we got before, bringing the module in, the volume in. And now I'm going to define the product of the total volume occupied by 1 mole of the gas times the density of molecules per unit volume. This thing is the total particles in 1 mole of substance. This is what we call the Avogadro number. Okay, so you know the Avogadro number, this 6 point whatever times 10 to the 24 or whatever it is. So it's a very large number, but it's just a universal constant. It's just there. Okay, so fine, just write it like this: 2/3 of the Avogadro number and the average kinetic energy. Okay, so on the other hand, we know that PV for 1 mole of ideal gas is the gas constant T. Okay, so we can just compare the right-hand side of the first expression with the right-hand side of the second expression, because they should be the same, because they are PB, both of them. So 2/3 of Na, the average kinetic energy, should actually be equal to RT. Okay, so if I then take how do I do it? Just a sec. Yes, so what I want to do is this: the kinetic energy, or the average kinetic energy per molecule in my system, is going to be 3/2 of R divided by Na times the temperature. Okay, and this thing, R divided by the Avogadro number. R is a constant, one of these universal constants. The Avogadro number is another universal constant, and the ratio actually makes a more fundamental constant. Okay, so this is the Boltzmann constant, and this is actually since 2019 it's defined to have an exact value of, and I put it in the lecture notes. I just copy it here just for fun. What is it? 0.649 times 10 to the minus 23 JK. So this is one of the fundamental physical constants, and it has a fixed, exact value. And this is used to define actually temperature scales and so on. So Boltzmann constant. This thing is actually Boltzmann constants. So what we have is 3/2 of KT. That's the average kinetic energy in 1 mole of ideal gas if we
model the molecules of this gas as structureless, point-like, not pointless, featureless, point-like particles of equal mass m. The average kinetic energy of those guys, if they are considered to be in thermal equilibrium, is actually 3/2 of the Boltzmann constant times the temperature. Now, just the same reasoning that we did before, right? So the average kinetic energy is going to, in the x direction, so the x contribution, 1/2 of the mass times the average velocity squared in the x component, is going to be the same as the kinetic energy contribution in the y direction, which is the same as the contribution in the z direction because of the isotropy argument that we said before. So this is actually 1/3 of the average kinetic energy of a molecule in total, right? So the contribution of all directions. So just using that in the previous expression, this is 3 times, well, this is something we know, they don't have to write this. So what I do want to write is that the average kinetic energy in any specific direction, x, y, or z, equals or contributes to the total with 1/2 of kT. That is 1/3 of this expression here because of what I just wrote here. Okay, so each degree of freedom of this system of these particles, x, y, and z, when in thermal equilibrium, contributes with 1/2 or receives 1/2 of kT energy on average. Okay, each degree of freedom of each molecule has on average this 1/2 of kT as kinetic energy. And this is going to be the starting point for the next video, which is the equipartition theorem, which we are not going to really prove, but we are going to state. And we are going to see the consequences of this for the remainder of this chapter. We are going to see that the equipartition theorem gives us a basis to calculate, or at least to estimate, heat capacities of different types of molecules, like monatomic gases, diatomic gases, when we consider vibrations or rotations and so on.